one last example of being able to solve an elementary differential equation, this time a second order differential equation, and it's also going to have some initial values to it. All right, so we have y double prime of x, 18x minus 60x to the fourth, y at 0 is 4, y prime at 0 is 0. All right, so we're essentially going to do what we did in the previous example to solve a second order differential. So we're going to say integral of y double prime of x is going to be equal to the integral of 18x minus 60x to the fourth dx. All right, now antiderivative of the second derivative, and this should be dx, is going to be y prime of x. Right? Antiderivative of 18x is going to be 9x squared. Antiderivative of 60x to the fourth, 60 over 5 is going to be 12x to the fifth, plus some constant of integration. And remember, this is the general solution, okay? At least for the first derivative, all right? So we can't even say that's the general solution yet, okay? But we have this initial value that y at 0 is 0. That means that x is 0 and y at x is going to be 0. So we just substitute those in. So y, or y prime of x, excuse me, since we're looking at the first derivative. So we get 0 is equal to 9 times 0 squared minus 12 times 0 to the fifth plus c, or 0 is equal to c. All right, and so that means that y prime at x is going to be 9x squared minus 15x to the fifth, or I'm sorry, minus 12x to the fifth plus 0, all right, because we just found that 0 was c, but we really don't need 0, right, since it contributes nothing to the sum. All right, now we're going to integrate again, all right, so now we're going to find the antiderivative, and that's going to be the integral of 9x squared minus 12x to the fifth dx, right? So we know that the antiderivative of y prime with respect to x of or y prime of x dx is going to be y at x. Antiderivative of 9x squared is going to be 3x cubed. Antiderivative of 12x to the fifth is going to be 2x to the sixth. And I'm just going to say plus d, all right? Because we've already found that c was equal to 0, I'll just use d. If I wanted to, I could use like c2 if I wanted to. All right. Now we go back up here and we recall that when y is equal to 0, that x, or I'm sorry, when y at 0 is going to be equal to 4. So when x is 0, y is 4. Okay, so y at 0 equals 4 means that when x is 0, y at x is going to be equal to 4. And so we substitute, all right? So we get that 4 equals 3, and we said that x is 0. Minus 2 times 0 to the 6 plus d. And clearly that means that d is going to be equal to 4. Right? And so we're going to substitute back in. Now remember, this is the general solution at this point. Okay. If we substitute back in, you get that y at x is going to be equal to 3x cubed minus 2x to the 6th. And instead of d, we have plus 4. And this is our particular solution. All right. Now, of course, we want to make sure that we have ways to be able to check our solutions. Okay, so I'm going to show you how to use Wolfram Alpha. Just remember, on an examination, you won't be able to use Wolfram Alpha or any other computer algebra system. So this is precisely what you're going to have to show on an examination. Okay, so just illustrating what you're going to do. All right, so this is our original differential, and just to type it in, I'll show you how to do that. So what you're going to do is you're going to type in solve. Y double prime is equal to, and remember we had the right hand side was 18x minus 60x to the fourth. Okay, and let's just say comma, or let's just go ahead and do that. All right, so if we solve that, right, notice what it does is it gives us this. Okay, so negative 2x to the 6th plus 3x cubed. Okay, and if we go back, okay, so we have our 3x cubed and our negative 2x to the 6th, but notice it gives us like this C1 and C2x. All right, that's because it's the general solution and we never put in the initial conditions. So remember, our initial conditions were y prime at 0 equals 0 and y at 4, or y at 0 was equal to 4. Okay, and so let's go ahead and run it now. And remember, we have negative 2x to the 6th, 3x cubed plus 4. So this is our particular solution. And then over here, we have negative 2x to the 6th, 3x cubed, and then plus 4. All right. And it also works with first order differentials. Okay. So if we go back up, remember we had this problem in the previous video. Let me just illustrate how to put that in and just to verify that you can get both the general and the particular solutions. All right. So if we want to solve that, we can say solve y prime is equal to, I think it was 2 plus sine of 2t, right? And let me just verify that, 2 plus sine 2t. And I'm just going to type it in without the initial condition first. All right. And so it gives us 2t minus 1/2 cos 2t plus c1. So we have 2t minus 1/2 cos 2t plus c. And it doesn't matter what we call c. It could be c1, d, c5. It doesn't matter. Now, let's put the initial condition, y at 0 equals 3 in there. So I'm just going to say comma, y at 0 equals 3. All right. And remember, we have this sort of thing right here. We might have to distribute, and I do believe we got 7 over 2. So if we distribute the 1/2, because you know how my math, or I'm sorry, you know how Wolfram Alpha works. Sometimes it does the factoring, especially with any computer algebra system. So we have the 7/2. We had 4t times 1/2, which is 2t, and the minus 1/2 cos 2t. All right, so it does work. Okay. Again, you should use this to check your answers, but you should absolutely be working through these so that way you know how to do all these when it comes time for the examination. All right, so after this is done, we have one more type of problem that we're going to work through, and that's actually going to be looking at what our differential equations look like in a Cartesian plane, and then also what the solutions might look like in the same plane.